AP Calculus BC, Lesson 5.3, connecting f prime and f double prime, first and second derivative, with the graph of f. So, challenging stuff. We're going to try and tie together some of the last two lessons. A little bit hard here. We got a lot going on, but what's going on here is when we're going uphill, f prime is greater than 0. Here, that's right, f equals 0. F prime equals 0. Here, f prime is greater than 0. Here, f prime equals 0. Here, f prime is less than 0. Here, f prime is undefined. Gotta watch out for that. Here, f prime equals 0, and here, f prime is less than 0. So we see how we can use the derivative to determine whether we have a increasing or decreasing function. But more than that, if you look in certain spots, the derivative is greater on one side, less on the other. That means we have a maximum. Might mean other things, so we got to watch out. So from positive to negative, our local max. Could be one of these two, but f prime is greater than 0. F prime is less than 0. Now I got the flip. If it's going down, f prime is less than 0. F prime is greater than 0. We have a min. Could be one of these. Could be a cusp, some corner like I'm showing. Prime is less than 0. F prime is greater than 0. If sign doesn't change, there's no extreme value. We have something called the point of inflection, or nothing. I mean, you have to look at the graph and figure it out. So this would be the point of inflection. This is where the derivative is not changing. On the way down, it could hit a little cusp or a corner, and the derivative isn't changing, so there's no min or max. Don't know if we call it anything. There's no derivative at that point. And then we have to deal with all the endpoints. We could have a local max. We could have a local min. And the flip side, we could have a local min, or we could have a local max. So we take derivatives. We see what the heck's going on. Take the derivative of this one, and we get 3x squared minus 12. We set it equal to 0. We get x equals plus or minus 2. Throw it on a number line. I'm doing this quickly because it's a very long video here, but we check and we say the derivative is positive, negative, positive by plugging in the numbers, say negative 4, 0, and 4. And then we know that we have a max because it goes positive down here. We'll just call it local, and a min. What about on the other one? A little trickier. The derivative is x squared minus 3 times e to the x plus 2x times e to the x, which is, we factor out the e to the x squared plus 2x minus 3 set it equal to 0, and we find zeros at -3 and 1. And our number line. Check it out, what's going on. Positive, negative, positive. So we get the exact same thing. And I strongly recommend throwing these up and graphing them before you run off. We have a max at -3. Turns out to be a absolute max, I believe. Or pardon me, local max. And I could say the max is at 1, and it exists of 1 comma, whatever the value is when I plug it back in. So watch out. What does concavity mean? This is concave up. And this is concave down. Now, as we say right below, we take a second derivative. That's what we talk about down here. And if the second derivative is greater than 0, making sure everything is differentiable twice, then concave up. Second derivative is less than 0, concave down. So, what's going on here on the functions? Y prime equals 2x, y double prime equals 2. This is concave up, because it's positive, on 3 to 10. I gotta make sure I say it right. Yeah. In the interval, here we don't include the endpoints. Here I get y prime equals cosine of x, y double prime equals negative sine of x, and graphing negative sine of x from 0 to 2 pi, we get something like that. And we'll say concave down from 0 to pi, pardon me, up, and concave down from pi to 2 pi. Concave down, 0 to pi. Did I draw it wrong? And I've got to go back to the original graph. It's negative, therefore it's concave down. And we're not talking about this graph, we're talking about the original graph. It's positive, therefore it's concave up. This is the far and away biggest problem people have with this unit, knowing which graph you're looking at and what you're talking about with respect to that graph. So, point of inflection. Function has a tangent, could be vertical. Or horizontal. More common for a horizontal one, but distinctly possible. And concavity changes. Derivative is 0. So we're looking for points of inflection on the graph here. Y prime equals e to the negative x squared, negative 2x. Y double prime's a mess. To save time, I'm going to blast it out. After we do it all and take the derivative, we find out 4x squared minus 2. So we say, what is 4x squared minus 2 equals 0? 4x squared equals 2, x squared equals 1/2, x equals plus or minus square root of 2 over 2. Number line it. Negative root 2 over 2, root 2 over 2. Alright. The derivative does one thing. The second derivative does something else. It is, I gotta plug it into the second derivative. If I put in 0, I get a negative number times this is always gonna be positive. This is negative. I put in anything greater or less, I'll get positive. So we have points of inflection at negative root 2, and this is where you get to go figure out where I got that from. Plug in negative root 2 over 2 into the original equation, see what happens. And root 2 over 2, and it should be the same thing, 1 over root e. And if you look at it, you'll say, yeah, okay, that kind of makes sense. Pretty tricky stuff. So look at this. Now, first things first, got to read the full question. This is the graph of f prime, derivative. So we've got from negative 4 to this first zero we've come across, negative 2. And you know what? It's easily drawing a number line. Find all the zeros. There's negative 2, there's 1, and then there's 4. 4 is the end of the line, though, so I'll treat it as if there's other end of the lines, but no. We are positive, positive, negative, and about to go positive. So if this is positive, negative, it is a max. If this is negative to positive, it is a min. And this is a point of inflection. How do I know? Because it goes from positive to positive. Has to be a point of inflection. I'd have to take the second derivative, and I can do that. Second derivative, I'll use negative 2, because that's a 0. Call it 0 even though it's not quite there. And 3, and say what's going on here. Slope is negative before that. Before negative 2, it's positive up to 0, and it's negative all the way down to 3, and then it's positive again. So, looks like there's more than one point of inflection. Definitely one here because it changes. Definitely one here, and definitely one here. Very, very, very tricky stuff. So you got to read up on it. You got to play with it, practice it, see where it takes you. Now we play with this whole thing, the particle stuff, and we find the derivative or velocity equals 6t squared minus 28t plus 22. And it turns out there are zeros at 1 and 11 thirds. I apologize for not showing you. Just don't quite have enough time. So we do this sort of thing. 1, 11 thirds. And we say it's positive, negative, positive. So this particle starts at negative 5 and it's moving to the right until t equals 1. I wanted to know what spot that is. I'd have to plug t equals 1 back into that. Then it's moving left. And then it's moving right again. What about acceleration? Well, we take another derivative. We get a of t equals 12t minus 28. 0 is at t equals 7 thirds. And we get a number line that, and we say the acceleration is if we plug in numbers, negative here and positive here, meaning that it's slowing down until 7/3 and then it's speeding up. Which makes sense if you look at this and compare it with this. The two together makes sense. Wish I could go into more detail. I don't have to do. Logistic growth looks like this. Use your calculator to plug it into the stat button. And all it's saying is that the growth accelerates. It has a point of inflection here at its greatest derivative. So f prime is greatest here. And that's its point of inflection. You need to use a calculator to find this. You can go to the second derivative and find where it's the highest. You can also go to, first derivative, find where it's the highest. You can also go to second derivative and find out where it equals 0. Challenging stuff. Actually modeling this is pretty easy. So you plug it into your calculator and see where it takes you. I'll make sure you read the question. We're talking about since 900 and is it in millions and all that sort of stuff. So it looks like Alaska's maxed out on its population. Who knows? Things could change. So here's the second derivative test. If the derivative equals 0, so you have a peak or valley, and the second derivative is less than 0, then you have a local max. We don't really need this. We just use the first derivative and we're good to go. But just to give an example, 3x squared minus 12 is the first derivative. Second derivative is 6x. Means that there is a 0 at x equals 0. So, find the local extreme values. Well, what's going on at x equals 0? Excuse me, we need to find the 0 here. So, x squared equals 4, so there's 2 zeros at plus or minus 2. And doing the second derivative, we're going to go with negative 2 and 2. Second derivative is at 0. Not very helpful. Oh, at negative 2 is negative. So according to this, less than 0, it's a local max. We could have done that just by going up here for this one and going negative 2 and 2, plugging it in and saying at 0 it's negative. Here it's positive. Here it's positive. So we know that's a local max. But we can also do it this way, plug in 2 and it's positive, so that's a min. Notice we're just doing it at the point. And I'm not a big fan. And last but not least, tie it all together. And I'm not sure if I'm going to do it. Nope. I'm going to leave that one for you guys. See where it takes you. I've got a little summary thing going on here, but you know, think about these things. And our derivatives could have custom corners. So we look at a graph of a derivative. Say, what could this possibly look like? And we say, well, this is the derivative, so the original graph, and we don't know where it is, top to bottom. We need a point to anchor it, so we're just going to run with this. It's a positive slope, but peaking out because it has a 0 and then it goes negative. Now it's a negative slope until negative 1. And then it takes off. It's positive right up to here, but there's no derivative here. But it's continuous according to the instructions. So, check out the next derivative. It's negative, so it's got to be going down. So let's make it a cusp just for the fun of it. Sure, it is a cusp. And then it goes positive again. Here, that's terrible. Here is the one where it changes over. And then it jumps to a negative. So this is a corner just for the fun of it. And stops at 4. And this is at 2. So notice it's continuous, not differentiable, which this already shows. It's got holes in it. And that is more than enough to keep you busy. Happy mathing.